Hello, today I'm going to present LamiFold. This project is a collaboration between Nadya Ramakers and myself, Leen. I will start with a quick impression of how LamiFold works, and later on I will discuss LamiFold in more detail. LamiFold allows for creating 3D objects with embedded functional mechanisms. We do this by cutting and stacking individual sheets inside the laser cutter and selectively applying glue using a stencil. This allows some parts in the stack to adhere together and others to move freely. After laminating, the scrap material surrounding the object is removed, revealing the designed object that can be folded into its intended 3D shape. The hinge locks the object in place, creating a desk lamp that's ready for use. With LamiFold, we make 3 contributions. First, we developed a set of parametric mechanical primitives. These 3 primitives result from our research on how to fabricate mechanisms using only stacked sheet material. All the LamiFold primitives are designed in such a way that they achieve their motion using only 3 selectively glued layers. LamiFold also offers an extensive support for customizing these primitives. Users can add unlocking mechanisms or select a detent option to restrict the movement to discrete steps, or adjust the orientation, size, angle, and so on. One option is, for example, to add a button to a sliding mechanism. This button compresses a laser cut spring, allowing the mechanism to move in the reverse direction. Another parameter is the shape of the notch that restricts the movement in 1 or 2 directions. Of course, the user can still reverse the direction by adding a button. We refer to the paper for more options. All parameters can be applied to our primitives, resulting in a wide variety of mechanisms. The second contribution is our custom design environment. This design environment facilitates previewing, customizing, and adding LamiFold mechanisms. Traditional CAD operation tools, for example, align and combine, can easily integrate our LamiFold mechanisms with the rest of the design. Testing and folding are done by pulling and pushing the handles that simulate the motion of the mechanism. The kinematic solver moves all connected linkages and shows the user how the object will behave. When exporting, LamiFold first checks for errors. For example, it checks for inconsistent layer thicknesses. With no problems found, LamiFold will generate the model's contours, taking into account that it is possible to remove all scrap pieces later. Last, LamiFold calculates a glue stencil by analyzing the regions where glue needs to be applied. Our third and last contribution is a novel fabrication workflow using stencils for selectively applying glue. Fabricating a LamiFold object starts by adding stock material, then we cut the model contour. Next, we add a temporary paper stencil and laser cut the glue contours. After removing all loose parts, we apply adhesive using a brush or spray can. After removing the stencil, the process repeats itself until all layers are cut and glued. The last step is to fold the object and secure all locking mechanisms, preventing it from folding back into its flat shape. Last, I want to talk about some limitations and future work. Creating LamiFold objects is often restricted by build size of the laser cutter. We think that future versions of LamiFold could mitigate this problem by automatically splitting large objects into smaller sub-assemblies. Because we use standard commercially available glue, a lot of different materials can be laminated. We think that further investigation into flexible and conductive material could generate exciting results. Lamination can produce quite some waste. To reduce this, a future version of our design environment could take scrap material into account and use it as part of the laminated stack. Last, we think that more primitives, such as primitives containing cylindrical and planar movement, could further broaden the design space. With that, I want to thank you for your attention.